Good afternoon, class. Today we're going to be talking about average rates of change, what a tangent to a curve is, and the slope of a curve, how to define that. We know how to find slopes of lines um, by just finding the change in y over the change in x. Well, today we're going to define how to find a slope of a curve. We're also going to define the normal to a curve, which is related to the slope of a curve. And then we'll talk about speed. The tangent line determines the direction of a body's motion at every point along its path. So our tangent line that we're going to be referring to today is a very important part of calculus. It helps us determine the rate of change. We'll first start with the average rate of change of a quantity over a period of time. Is to divide the amount of change by the time it takes. So in general, the average rate of change of a function over an interval is the amount of change divided by the length of the interval. The average rate of change can be thought of as the slope of a secant line. So we'll have to define a secant line here as the line that connects two points on a curve. So if we had a parabola here, just in general, and -2 may be here, and x equals -2, and x equals 4. This is an interval, not an ordered pair. So remember, we refer to intervals as a length of an interval, and this is the x. So if x equals -2 is here and x equals 4 is here, the secant line would be the line that connects those 2 points. So that's what we're going to find as the slope to that. So to do that, we're first going to need to find what f of 4 equals and what f of -2 equals. Because if you remember, to find a slope, that's what we're trying to find here. The average rate of change is just slope, so you can write that up here. It's just a slope of a line from -2 to 4. We need to find the two y values that correspond to these two x values. So we're just going to simply put 4 into x in this equation. So we will have 2 times 16 minus 12 plus 7, that'll be 27. And then we'll put -2 in. And we'll get 21. So here is our y value. So think of this as y2, and this is y1. Think of this as x1. And this is x2. So we end up having 2 points that we can find the slope of by doing 27 minus 21 over 4 plus 2. So we're going to get 6 over 6, which has a slope of 1. So this is the average rate of change over this length from -2 to 4. So that's a secant line. In calculus, we refer to, or we want to find the tangent to a curve. Well, in calculus, we often want to define that rate at which the value of a function y equals f of x is changing with respect to x in any particular value, x equals a. And we're going to have that be the slope of the tangent to the curve y equals f of x at x equals a. The problem with this is that we only have 1 point. If you think about slope, we need to have a change of 2 points. So we're going to have to find a way to define that. The process becomes, we'll start with what can be calculated. So we'll find a slope of a secant line somewhere on our curve. Just between 2 points, call them P and Q. We just want Q to be relatively close to P. We don't want it to be too far away. So we'll find the limiting value of the secant slope. So as what that means is as we take and move Q closer and closer and closer to P, we're going to define that slope of that curve at P to be the number we get when we move that Q closer and closer to P. So this is what it looks like. So we'll have a point Q out here and a point P here. So the black line here is referring to the secant line. So the slope of that secant line can be calculated by taking the change in y, so that would be f of a plus h minus f of a. So that's this here. So that's your change in y. And then our change in x will just be a plus h minus a, which is just h. Well, what we'll do is we'll just keep making h smaller and smaller so that we can move our point Q closer. So we could start here with it and then keep moving it closer and closer, and eventually get it so close that it then approximates the slope of this line, which we're going to refer to as the tangent line. So this line here is called the tangent line. So we're going to find that slope. To do that, we need a formula. So here's the formula we're going to use. We're going to do this for the function f of x at x equals a, and the slope of the tangent at that point. So this is going to be called the instantaneous rate of change of f of x with respect to x at x equals a. So as I was saying, we're going to have the change in y, so that's going to be f of a plus h minus f of a all over h. And we're going to take the limit as h approaches 0. So we're just going to keep moving it closer and closer. So this expression here is the difference quotient of f at a. So let's do an example. Say we had y equals x squared plus 2, and we wanted to find the slope at x equals negative 1. So we could write an equation to a tangent line. So we're first going to have to define these two things, f of 1 and f of 1 plus h. So this a is 1 in this case. So we're going to have to put that into our equation. So this is a composite of functions. So we're going to put, let me back that up here for a second. So this will equal 1 plus h squared plus 2. So we're just putting 1 plus h in for x here. F of 1 will just be 1 squared plus 2, which is going to be 3. So we now have, I'll extend this a little bit. So we now have our two y values. So we're going to have 1 plus h squared plus 2 minus 3 all over h. And we're going to take the limit as h approaches 0. So we can't actually put 0 in here yet because that would make the function undefined. So we can expand to this though, and that's what we're going to do next, is we're going to expand that. So we'll get 1 plus 2h plus h squared plus 2 minus 3 all over h. You can see that we're going to get 1 plus 2 minus 3, so that will go away, and we'll get 2h plus h squared all over h. Again, we're taking the limit as h approaches 0 for this. We can see that we can factor out an h, so we can reduce that down and just get the limit as h approaches 0 of 2 plus h, which now we can put 0 in because it does not make it undefined, and we get the slope as 2. So the slope can now be used in an equation for the tangent line. So this is the process for that. So I'm just, I have it already put in here in the slide here. So this is just the point slope formula. So we would do y minus y1 equals, and then think of this as m. I lost a negative there somewhere. Let me go back. Oh, that was -1. There is my problem. You're just going to have to put a -1 in there for your slopes, because that'll make this a -2h here. I apologize, I wasn't even paying attention that had been a negative. So this whole slope ends up being -2. So I just had a negative here that I was missing in my problem. So it didn't change the value of this here because we were squaring a -1. So that wouldn't have changed that. It just changes this middle term here. So now we can come over here and we can write our equation to our tangent line, y minus y1. So think of this as the y coordinate. M is the slope, and then x minus x1. So we end up with an equation to the tangent line being y equals -2x plus 1. So we'll do some practice problems for this tomorrow in class. So we'll see how well you understand it.